Okay, so the topic is I'll introduce the concept of random matrices, and before that, I'll give some motivations for studying random matrices. So it first arised in nuclear physics, and it was introduced by Wigner, who was using a random matrix to model the nuclei of heavy atoms. I also don't know much about this, but the thing is, uh, the statistic that he was trying to study is related to the eigenvalues of a random matrix. So we are kind of interested in the eigenvalues of random matrix. Secondly, it was first noticed by Wishart in the statistics, and I will explain what matrix he considered. So suppose we have n IID random vectors. IID means independent, they're all independent and identically distributed. The distribution of all the random vectors are the same. So what is P here? P is the dimension of the data observed, and N is the number of samples. Since we have N random vectors, how do we collect them and study at once? What do? We form a matrix X, whose columns are X1, X2 up to Xn. Then we create a matrix known as sample covariance matrix, which we might have seen in like statistic courses, which is defined as 1 over n x transpose, which is, you can see, is a P cross P random symmetric matrix. And we can study this to inference, like to infer about like properties of large samples. Okay, the last one, I think, which Sampurna and Badri might know more, is the applications in number theory. Which one? This one, I think I've read somewhere that the distribution of zeros of the Riemann zeta function and other L functions is modeled by the distribution of eigenvalues of certain random matrices. So the zeros are somehow related to the eigenvalues of certain random matrices. So it's worth studying random matrices, and I'm sure there's many more applications of these. The one which I know of is combinatorics, and I will discuss this later in more detail. Okay, so what is a random matrix? Random matrix is any matrix whose sum of the entries are random. But we cannot study general random matrices. We need to introduce some structure, and that's what we'll do now. So I'll mainly discuss 3 examples of random matrices, and we'll see how do their eigenvalues behave. Okay, so the first one is a Wigner matrix. I'll define what it is. There's also a complex Wigner matrix, but in this talk we'll focus on real Wigner matrix. So real Wigner matrix is any matrix which is symmetric. So the first condition is it is symmetric, and all the off diagonal entries are IID, means independent and identically distributed. All the diagonal entries are IID, and overall all the entries are independent. So this is symmetric. Off diagonal entries are identically distributed. Diagonal entries are identically distributed, and all of them are independent of each other. And the last condition is to make the model more simpler, is to assume that the expectation is 0 and the variances are finite. So yeah, in this case, suppose we have to write the density function. What we can do, since all of these are independent, we can just multiply the density function of each of them to get the joint density function. So there's some other example, but I'll discuss this later. I'll first discuss how the eigenvalues of this Wigner matrix behave. So first we'll just focus on Wigner matrix. Okay, I'm not gonna give a proof of Wigner semicircle law, but I'll try to motivate the statement. So before we can find the limit theorem, if we know that suppose the eigenvalues behave like, say, n to the power alpha, to get the limit theorem, we have to scale it by n to the power alpha. So let's first try to find out the order of the magnitude of the eigenvalues. So since the Wigner matrix is symmetric, its eigenvalues will be real. So let x1 up to xn be the real eigenvalues of n cross n Wigner matrix. And since we want to consider the magnitude of the eigenvalues, we'll square them. So what I'm doing here, I'm taking the sum of xi square, which if you notice is exactly the trace of matrix square, which I can further compute like this. Now I will take expectation. So expectation distributes in sum. So summation of expectation is equals to expectation of this. But as we assume for a Wigner matrix, the diagonal entries are identically distributed. So this is just n times expectation of that. And we know that off diagonal entries are also identically distributed, and there are n times n minus 1 divided by 2 of them. So we can see that the right hand side is order of n square. Okay, now this is just some heuristic argument. So let's assume that all of these eigenvalues behave in the same way. That means n times the order is equals to order of n square. Then we divide by n. So what do we get? We get expectation of eigenvalue square is it equals to order of n, which will give that the eigenvalues behave like order of square root of n. So this is just a heuristic argument to justify somewhat the statement of Wigner's semicircle law. Okay, now we know that eigenvalues behave like root n. So we should scale our original matrix, which is equivalent as scaling the eigenvalues. So now I will define the scaled Wigner matrix, which is m is equals to 1 over sigma root n times h, where h is an n cross n real Wigner matrix, and the variance of the off diagonal entries is sigma square. So now I will say that the eigenvalues of this scaled Wigner matrix is lambda 1 up to lambda n. Then I know that these are order of 1 as n goes to infinity because I've scaled by square root of n. So now they are order of 1. Okay, so instead of considering the Wigner matrix, we'll consider the scaled Wigner matrix because of this reason. All right, so now we have n eigenvalues, but I want to study all of them together because as n becomes larger and larger, we'll have like millions of eigenvalues. We cannot like study each of them separately. And the way to do that is to consider what is known as empirical measure for any number of random variables. So I'll define what is empirical measure. So empirical measure of random values x1, x1 up to xn is the random discrete measure. I will explain what it is on R given by this 1 over n summation of all the indicator functions of xi. So what it means that okay, yeah, I'll show this later also. So this is a convenient way of encoding the collection of all the random variables. Okay, so and how do we define the empirical measure of the eigenvalues? It is defined the same way. So since the matrix is random, the eigenvalues are also random. So lambda I are nothing but the random variables. And so this is the same, just xi is lambda I. So let's see few of its properties. So the mass of this measure is 1, right? Because mu n of R is equals to 1 over delta lambda I n of R. Since all the eigenvalues lie in the real line, all of these delta functions will be 1, which will give n divided by n, which is 1. So this is a probability measure. And let's see more properties, how the integral is defined. So if we integrate this function with respect to this measure, since this is a point mass, we know that It just evaluates the function at lambdas and then averages them. And the special case is, say, if I take f is equals to indicator function of an interval, then the left-hand side is the measure of that interval, which is 1 over n times the number of eigenvalues that lie in that interval. So is it clear what mu n is? Okay. So we'll try to study this. Any question? No, okay. So we'll try to study this empirical measure, which encodes all the eigenvalues. And here's the figure which I've stolen from my lecture notes. This is how the distribution of eigenvalues look like. So this is some kind of random matrix. This is a Wigner matrix. I will explain what GU is later, but this is a random Wigner matrix. And the dimension is 2000 times 2000. And if you see the distribution of eigenvalues, this is a histogram. It means that the number of eigenvalues which lie between 0 and say 5 is the height given by here. So you can see that this histogram converges under proper scaling to some kind of semicircle measure. And that's what the statement is. So before that, let me define what a semicircle measure is. So semicircle measure is the measure on R that is given by this. So the density function, the graph of density function is just a semicircle based on -2 to 2. Okay. Now I'll state the semicircle law. So let's recall what is a Wigner matrix. Off diagonal entries are all identically distributed. Off diagonal entries are all identically distributed, and they are all independent. So since the diagonal entries and off diagonal entries are IID, I just need to consider one of them. So I'll say let h11 and h12 be independent random variables. I have to assume that mean is 0. And I'll assume that the variance of the off diagonal entry is sigma square. And obviously the other one is also finite. Now I'll consider a Wigner matrix, which is given by this. H of n is hij, ij less than n1. Even though I've not defined what are other entries, but we know that those are like all the other diagonal entries are distributed like h11, and all the other off diagonal entries are distributed like h12. So I know what my Wigner matrix is. As we discussed, we have to consider the scaled Wigner matrix, which is m is equals to 1 over sigma root n. And then we consider the empirical measure for the eigenvalues. Empirical measure is just this. Wait, what happened? What? Okay, good. Then the statement is this measure convergence in some sense to this semicircle law, this semicircle measure. And what does this weakly almost surely means? So remember that this mu n is a random measure. So if I integrate some function with respect to random measure, I will get a random variable. So you can relate it to this. So what does this means? That for any continuous bounded function, the sequence of random variables, when you integrate f with respect to du mu n, converges to f with respect to sigma semicircle law. But this is a convergence of random variables. So we have to specify some kind of convergence. I am saying almost surely. So weakly denotes that this converges in terms of like with respect to some continuous moderate function, and almost surely concerns the convergence of random variables. So this is what the statement is. I'll not go into the proof, but I'll tell you there are three different kind of proofs. The first one is, and the three of them are like very different. The first one is combinatorial proof, in which I also don't remember much, but in which we have to consider some trees and there's some moment method and you have to use that. That is more combinatorial. The second one is analytic method, which uses Cauchy transform and those things. And the third one is a proof from potential theory and uses energy minimization law. And the proof is not trivial. So I'll make no attempt to prove this. Okay. So for Wigner matrices, we have a well defined description of the eigenvalues. This is how the eigenvalues behave. And we, for now, just care about the eigenvalues. Okay, let me go back to any question for the first part. Okay, if not, then I'll discuss the second type of random matrices. So Wigner matrices was some other collection. Now I'm going to consider some different collection. Again, you can see the space is the same. I'm still considering n cross n symmetric matrices. So that is my space. Okay. I didn't write this. So we know that the space of symmetric matrices is nothing but r to the power n plus 1 divided by 2. That is the dimension of the space of symmetric matrices. So the space is the same. So I've given you the space. Since it is equivalent to some Euclidean space, the sigma algebra I'm going to consider is Borel sigma algebra. And so we have a probability space, we have a sigma algebra, and I am equipping this space with a probability measure of this form. So the probability measure looks like pH dh, that this is the density function, is equals to 1 over c e to the power minus trace v of h, v is some polynomial, I'll tell more about that later, and dh. So this is the density function. Okay, what is dh? dh is just the Lebesgue measure on its variables. Since it is symmetric matrices, these are the off diagonal entries and these are the diagonal entries. And this is just a product Lebesgue measure on the usual measure on Euclidean space. And what is C? Since this is the probability measure, C is the normalization constant, which means that C is equals to the integral of this part. Okay. What is this function V? So this function V is a polynomial of even degree whose leading coefficient is positive. Why do we require this? So that this VH decays properly in the infinity. Even degree will ensure that it has the same behavior at both sides, and positive will ensure that it goes to 0. So this is the one of the ensemble of matrices. So this is called orthogonal ensemble. We don't see any orthogonality here, but I'll tell you what do we mean by orthogonal ensemble. And I've also given a hint why it is called orthogonal ensemble. It is actually orthogonal invariant ensemble. Okay, so now our aim is to understand why this is called orthogonal invariant ensemble and just see a theorem describing the eigenvalues of these kind of random matrices. Okay. This is the issue. Okay. Okay. So I wanted to do some computations, but not some like uh, very like frustrating computation. So let's consider a simple potential. Yeah, Vx is called the potential. So let's consider the simple um, example of the potential, which is x squared by 2, which is called the Gaussian orthogonal ensemble, and explain why. So let's try to compute its density function. So density function is 1 over c e to the power minus half trace h square. And now we know that trace h square, this you can verify, it's not difficult to verify, is this, and then you can write like this, and using the symmetry you can like this. So this is what I'm going to use. So using symmetry you can write like this. So now this density function becomes, sorry about this, this should be c. Okay, it's not working. So I'll just replace trace of h square by this expression. So when I do that, I get minus half hjj square. This summation becomes the product. And then this 2 and 2 cancels, and this becomes e to the power minus hjk square. So remember that if you have a joint density of some of the random variables, and you can factor out, like you can clearly see that the joint density of x1, x2, xn is some density of x1 times some density of x2 times some density of xn. That means that the random variables are independent because it is a product of the densities. So in this case, we can see that we can separate each of the variables. That means it is independent. And you can just look at hjj. It looks like the density of normal, right? It looks like the density of normal distribution. So of all the diagonal entries are distributed like normal 0, 1. And there's some like change of variation in the off diagonal entries, but they're still Gaussian. So they are distributed like normal 0, half. So what is this? This is nothing but a Wigner matrix, right? Because it is symmetric. All the entries are independent. All the diagonal entries are identically distributed. All the off diagonal entries are identically distributed. Expectations are 0, and the variances are finite. And in fact, one can show that, and again, it's not an easy result, that the ensembles of Wigner matrices, like we consider the Wigner matrices, and then we consider the orthogonal ensembles, they intersect only in GOE, only when Vx is x squared by 2. Sorry, when Vx is x squared. So they just intersect in one model. Otherwise, they are like very, very far from each other. It is not true that the entries of orthogonal entry ensemble are independent. So they are indeed different. So it is worthwhile studying orthogonal ensembles. Okay. Now let me show why it is called orthogonal invariant ensemble. This is because this probability measure, which I defined earlier, is invariant under orthogonal conjugations. So let me remind what is the, I think it's not a good idea going back up and down again. So yeah, here it is. So I have to show that this measure is invariant under orthogonal conjugations. And that's what I'm going to show, and which will justify the name orthogonal ensemble. Okay. Okay, that's what I'm trying to do now. Okay, before we do that, I'll identify Sn with Rn n plus 2 in such a way that their inner products also match. Okay, so if I have a matrix in symmetric group, then I can identify that matrix with this vector. So first I'll list all the diagonal entries. Then I'll list all the entries of the first row except the diagonal entry. Then I'll list all the elements of second row except the diagonal entry. And then finally, the last, like the hn minus 1 comma n. So this is a vector in Rn plus 1, 2. Now I have to somehow make sure that the inner products are same. We'll see why we want to do that. So what is a natural inner product on the set of matrices? So on the set of matrices, the inner product is trace of A B transpose. But since the matrices here are in symmetric, that transpose goes away and it is given by trace of AB. And again, if you do calculation, this is again not difficult. If you find what is trace of AB, it is given by the summation of product of the diagonal entries and 2 times the product of the off-diagonal entries. And this is the claim that this inner product, the inner product of these matrices, is same as the inner product of vectors A and B, but with some matrix D. But it's not difficult to identify what is matrix D. So we see that to get this from here, the first n entries just multiply to each other. So the first block of D should be identity, the first diagonal block, and the rest of them multiply with a factor of 2. So the other diagonal matrix should be 2 times identity matrix. And that's what it is. So it is In and it is 2In n minus 1 by 2. So if I take D to be this, then these two inner products are same. And we'll use this fact to show that the measure is same under orthogonal conjugations. So I've recalled what is the distribution. It is 1 over C e to a minus trace VH dH, where dH is just the product measure. So it has 2 parts. The first part, 1 over C is not, it is of course unchanged. So we have to show that this is unchanged and this is unchanged. So first I'll show that the simpler part, that e to the power minus trace VH is unchanged under the conjugation. So let's consider an orthogonal matrix. Then trace of V of O transpose HO. So remember that V is a polynomial. So suppose I have some coefficient like x to the power n. So if I do O transpose H O to the power n, then by using the orthogonal properties, I get this. Yes, I should close some things. It is.
एकदम चार्जिंग में शायद लगा दो तो उससे बेटर हो जाए.
Oh. Karthik. Okay, so we see that if I have a monomial x to the power n, if I do O transpose HO to the power n, I get O transpose HNO. So we see that this O transpose and O come out. And then by the properties of trace, we know that the trace of conjugations is same as the trace of the matrix. So this part is unchanged under the orthogonal conjugation. Now I have to check whether this measure is unchanged under the orthogonal conjugations. So what is our map? So I've taken a matrix H and it goes to matrix L, which is O transpose HO, I have to show that DL is same as DH. So first of all, notice that this transformation is a linear transformation in matrices. And so there exists a matrix of dimension n plus 1 by 2 such that vector L is same as A times H vector. Okay, now I'll show why. Okay. So let us assume that so I didn't write this, but L1 is AH1 and L2 is AH2. Okay, so I'll start with this H1 inner product with this part. Then I'll take this A transpose here. It will become AH1 vector, D AH2 vector. But AH1 vector is nothing but L1 and AH2 vector is nothing but L2. That by this inner product, remember by our identification, is same as inner product of the matrices. So this is nothing but L1 inner product L2 but of matrices. Now I know that L1 is given by O transpose H1O, O transpose H2O. Again, you transfer O transpose here and there and everything cancels out and you get H1 comma H2, which again by that identification is H1 vector comma D H2 vector. And this holds for all H1 H2. So if you compare these two, the first and last inner product, we get that A transpose DA is equals to D. Both of these matrices should be same. And when we take determinant of this equation, then we get that determinant of A times determinant of D times determinant of A is equals to determinant D. Determinant of D cancels, and we are left with determinant of A square equals to 1, which gives that the absolute value of determinant A is 1. Since this is a linear transformation, Jacobian is absolute value of determinant of A, which is 1. And so DL is equals to DH. So we have verified that this probability measure under the conjugations remains unchanged, and hence the name orthogonal invariant ensemble. Okay, so now we have justified the name. Let's see how does the eigenvalues behave. Again, I'll not prove the result. So if I denote by lambda 1, lambda 2 up to lambda n the eigenvalues of orthogonal ensemble, this is how the density looks like. Okay, so it has two parts, right? So the first part is this product of lambda k minus lambda j. So what happens if the eigenvalues are very close? This implies that the density function is very small, right? If the eigenvalues are very close to each other because of this factor. So that implies some kind of repulsion, that eigenvalues are not close to each other. The second part is the product of exponential minus v12 lambda j. If lambda j is very, very large, v lambda j is very, very large, and hence e to the power minus v lambda j is very small. So it says that lambda j's are also not too big. So there's a repulsion factor and also a confinement factor. So that's what I've written here. So this factor gives a pairwise repulsion, and this implies confinement. And this is not only true for this ensemble. There are several other ensembles which follow the same properties, that there are some pairwise repulsion and there's also confinement due to the potential. Okay. So I said in the beginning that I'll explain more a deeper application in combinatorics. But before that, I have to introduce something known as unitary ensemble, which is not much different from this orthogonal ensemble. It's just you can see what's happening here. So everything will change to complex numbers. So again, instead of symmetric matrices, the set is of Hermitian matrices. Then an analog of symmetric matrices are Hermitian matrices. But now this is equivalent to our n square, as there are n square independent variables. And the probability measure is again of the same kind, 1 over c e to the minus trace vh dh. So now remember, there are n square variables, the real part of off diagonal entries, the imaginary part of off diagonal entries, and the diagonal entries, which are themselves real. And so this is not much different from orthogonal ensemble. And as you can guess that this, if you conjugate this probability measure by unitary matrices, this is unchanged. And the density function for this changes a little, there's a small change, but it makes a huge impact. I've studied so many theorems for unitary ensemble, but there exists no such theorems for orthogonal ensemble. What it does in case of unitary ensembles, it creates a factor of 2. And as you can as you can see that, yeah, I don't want to go into deep, but yeah, so this helps a lot in analyzing these kind of models whenever there's a square. So people most of the time study the complex version of random matrices, so they get square, and it's all the same studying them. Okay, so as we had, remember, GOOE, which is Gaussian orthogonal ensemble, when we took Vx equals to x square. Similarly, we have GUE when we take Vx equals to x square. Okay, so now I'll state a theorem which will tell how the largest eigenvalue of n cross n GUE matrix behaves. And the result is, if you do the proper scaling, if you shift it by factor of root 2n and then scale it by this factor, then it converges to a random variable x. You should see this like central limit theorem, right? You have Sn, then you subtract the mean and divide by variance, then it converges to normal. It's a similar result. So if you properly scale, it converges to a universal, I should say universal, even though I'll not show why it is universal. It converges to a universal random variable, which is known as, which follows GUE Tracy-Widom distribution. And so this you can think of just a central limit theorem. Again, this is very hard to prove. This factor of 2 helps it to write in terms of determinants of orthogonal polynomials, and then they use some kind of properties of orthogonal polynomials. Then those polynomials are actually Hermite polynomials, and for Hermite polynomials they do steepest descent, and they do several things to get this result. But I'll not go into that. I'll show that why this x is universal. Why I'm saying that this x is universal. Does it appear in other places? Actually, it appears in a lot of places. So that's how it is related. There are some models in mathematical physics whose distributions arise from the random matrix theory. So this x will appear like in a lot of other models. So one of the deterministic problems I will start with. So this is called the Ulam's problem, which is very simple to describe. So suppose we have a symmetric group Sn. We consider any permutation pi, and for any subsequence of indices, if the corresponding pi I1, pi ik is increasing, then we say that this is increasing subsequence of length k. Right? So suppose you have a subsequence, you just see you just find any increasing subsequence of that. That is just increasing subsequence. Okay. So what is ln pi? Ln pi is the length of the longest increasing subsequence. Okay, so this is, I've taken one example in S9. So this is the permutation 4, 1, 3 up to 6. And let's try to find what is the largest increasing subsequence. So if you see just by observation, you will find that 1, 2, 5, 7, 9 is one of the largest increasing subsequence. Of course, after 7, you could have gone to 8. So largest increasing subsequence is not unique, but length is unique. And you can see that length is 5. So Ulam's was idea to study this length, and it is a very deterministic problem. There is no randomness here, but it turned out that it is very difficult to study this deterministic problem. And in most of cases, what they do, they randomize it. What do you mean by randomizing? They equip Sn with a uniform measure, which is the simplest measure. Since there are n factorial elements, I will give each permutation a measure of 1 over n factorial. And so now it becomes a probabilistic question. So first, it was shown that if you take expectation of ln divided by root n, it converges to 2, which is a big result, because they weren't able to prove that ln behaves like 2 square root of n. Now, just by inducing the probability measure, they have this result that ln behaves some like 2 root n. And moreover, this was the big result, which is again like the central limit theorem. Central limit theorem completely describes the random variable, the behavior of random variable. It says that ln minus 2 square root of n, if you scale and shift properly, it converges to the same random variables, which describes the largest eigenvalue of a GU matrix. So somehow the largest eigenvalue of a GU matrix is related to the longest increasing subsequence. And this can be used in several ways. So yeah, this is the conclusion, that the length of the longest increasing subsequence of a random permutation behaves statistically like the largest eigenvalue as n goes to infinity. And these kind of results are very important in probability. Suppose you can say that this behaves like this, then you can well study one of the models and you can infer about the other. And this is true in a lot of physical mathematical models, and also one problem in combinatorics known as tiling model. In all these kind of combinatorial and probabilistic models, you will see this GUE Tracy Widom distribution at some level. It generalizes to something else, but yeah. So this is why it is universal, and it happens all the time that distributions that arise in random matrix theory somehow are related to the distributions which are the limit of some physical models. And not for all it is justified like why they're related, but for some people can explain why this model is related to that. Okay, so to summarize, I think that's when I finish, but I'll summarize. So we saw 3 examples. The first one was Wigner matrices. We saw that the eigenvalues, the empirical distribution of eigenvalues converges to semicircle law, which describes the behavior of eigenvalues. Then we saw orthogonal ensemble, which is invariant under orthogonal conjugations. And we saw the density of their eigenvalues. And then we finally discussed this GUE and how the distribution which arises as the largest, as the distribution of largest eigenvalue is the same as the distribution of the longest increasing subsequence. Okay, I think that's where I stop. I didn't write more. If I try, I can write more, but yeah, I think I'll stop there.